G'day, I'm Dr. Kev, and we've been designing a car based on 1950s sports cars. In the 1950s, sports car designers were focused on trying to reduce drag of vehicles. This ended up with streamlined looking cars. But these cars look very different to the cars of today that make good use of aerodynamic tools and analysis. So I needed to know, could you still make a 1950s inspired car that had reasonable aerodynamics for the road? Welcome to Car Design Workshop. Early in the process of designing Project 171, I developed a few car body shapes to investigate whether I could do the modelling process and pull off something that was going to look close to a 1950s sports car. But since those early efforts, I've mainly been focused on the internals of the vehicle, things like the suspension, the structure, the arrangement of all of the components, including things like the ergonomics. I figured that I needed to sort this stuff out before I could go back to working on the bodywork. There was no point trying to design bodywork with dimensions that were just not going to work with an overall vehicle. The plan was definitely to go back to the aerodynamics and spend a fair bit of time trying to figure out the design of the vehicle, but the plan was to do that quite a bit later. That is, until I got contacted by the good people at AirShaper. Now, if you don't know, AirShaper is a company that offers CFD services online. So CFD being computational fluid dynamics. And this is a way to simulate the aerodynamic performance of your vehicle. If you follow some of the same YouTube channels that I do, you would have seen Superfast Matt has used AirShaper in the design of his high-speed vehicle, as well as Robin Shute with his new hill climb car. I had intended to give AirShaper a go at some point, so when AirShaper contacted me, thought this is an opportunity that's too good to pass up. The only problem was, I didn't really have a model that was suitable to run in the simulations. A lot of the earlier bodywork that I had created no longer fit with the internals that I'd been working on. But unwilling to let the opportunity pass, I thought, let's give it a shot. So I went away and spent a fair bit of time modeling a body that was closer to where the thinking of the project was at the time. This was informed partly by the scan that we had done of the Austin Healey, as well as the early bodywork designs and the work that we had done on the structure of the vehicle. In a phone call with AirShaper and their CEO, Wouter, I was encouraged to put as much detail in the model as I could. Now, I was fairly doubtful of this. I have done some CFD in the past, and generally, I've had to use models that have got reduced simplicity just so you can get a decent mesh. Now, I want to be clear, what AirShape has provided for this video is access to their software, access to their platform. The channel is not receiving any money from this arrangement, and AirShaper has no editorial control over this video. I made it clear that we're always going to try our hardest to be as honest as we can with the tools and techniques we use on this channel. Now, I needed to lay that out because if you see the rest of the video, you'll see that I've been massively impressed with the product and process that AirShaper have provided. Now, I have a few aerodynamic goals for Project 171. If we look at the top level, we can think about drag and lift. I wasn't really worried about drag. This is a car that's not intended to be a competition vehicle, and it should have more than enough power to have reasonable speeds. When it comes to lift, however, I'm a little bit more concerned. So a lot of the 1950s and 1960s vehicles, while they were designed for low drag, they didn't really have much consideration towards lift. And if we look side on, a lot of these cars have the rough general shape of an airplane wing. What that means is a lot of these cars had considerable lift. Now, lift also has an effect on balance. So if we have a fair bit of lift at the front end of the car, we can lose steering authority. If we have a fair bit of lift on the rear end of the car, then we can have a car that will oversteer at speed and become quite unstable. So when it came to lift, I wanted to make sure that the vehicle was fairly neutral, didn't really have lift, didn't really have any downforce, and if anything, a slight amount of downforce with more at the rear than at the front. Now, another issue that I was concerned about is yaw stability at speed. But this is something I'm going to leave for another video. Now, one thing I was very concerned with was the noise and turbulence that would be hitting the driver's head. Having gone on long trips in a 1950s sports car, the Austin Healey, it can be quite noisy and you feel a fair bit of turbulence on your head. And this takes away from the enjoyment of the drive. So I thought a really good starting use for AirShaper was to see how close was I going to be to these goals. In order to start the process online, they needed to upload an STL. That's a type of 3D model, and it's reasonably easy to export that from SolidWorks. When modeling the bodywork, I did take some time to make sure that it was all watertight and suitable for scaling down and 3D printing. This meant that the bodywork was a reasonably straightforward shape to do some analysis on. But I wanted to test Wouter's claim about just building in complexity. So when it came to all of the other parts of the car, I just exported the STL of my main assembly. And this STL is an absolute jumble. It's got absolutely everything in it. It's got the suspension in it. It's got little pipes that I'd been running, the whole lot. It wasn't a specifically made CFD model. I was fairly confident that I was going to have to come back and simplify this model to make something more suitable to upload. Once uploaded, there's only one real setup page to go to. You choose the simulation type, so is it on the ground, above the ground, static, moving, is it in air or water? All of that is fairly self-explanatory. And then there's a choice of velocity. Now, given that this is a road car and a fair amount of the time you're just going to be cruising, I thought I just want to see this car straight ahead at 100 kilometers an hour, which is a fairly common speed on the roads around Perth. Now, when I had imported it, the car was facing the wrong way. So I needed to rotate the model. Now, it's pretty important that you set the reference of this after you've rotated. And I can't tell you exactly how I know this, although I do have results of the car traveling backwards. The only other things are model units, so millimeters, it's the only real unit that makes sense, and the overall model scale. Now, there's a couple of other things that I wanted to define. First, that this will be able to auto-detect wheels. Now, as I said, the model as it was uploaded was pretty complex. It had the suspension and everything in there, and I was fairly doubtful that it would be able to pick out the wheels reasonably easy. But I was pretty surprised. It was straightforward, selected the wheels, rotating in the right direction, and rotating at the right speed. Now, the only other thing that I wanted to define was the radiator at the front. I was fairly keen on seeing how the air would move through that ducting, especially how it would interact around the windscreen and driver and so on. So for this, you need to define two velocities and a pressure drop for each. I didn't have very accurate numbers there. I just went on something that seemed reasonable from the internet, but that's something that'll have to be updated as we get a bit more detail on what the radiators are likely to do. The next step is to order the simulation. And there's a few options here. So there's a basic accuracy, a regular accuracy, and an advanced accuracy. And each of them costs a different amount. So a basic run is 1 credit, a regular run 10 credits, an advanced run 50 credits. And that is based on the number of cells in the CFD. These number of cells is how much the air is broken down into. If we break it down into more cells, we can get a more accurate simulation. Now, given there was a fair amount of detail, I thought I'd go with a regular run, also noting that this is pretty early on in the design process, so there wasn't really a need to waste the resources of doing a particularly long run. Now, I probably could have got away with using a basic run at the beginning, but I really wanted to see what this software could do. Now, there was another option, which is to do some design advice, and that's where you could get the software to tell you what areas of the geometry need to change to reduce or increase drag or lift. So I just kept it simple, put it on regular, started the simulation. Now, this is a pretty complex calculation and it takes a fair bit of time, and the run time for the first simulation was between 4 to 8 hours. And when I opened it up, I couldn't believe that it had just worked. All of the issues in the past with CFD have really involved trying to get a decent mesh and getting that to run. This just worked. It had rotating wheels, it had a radiator in it, it had reasonable results. Having done this sort of stuff in the past, this just blew me away. And there's pretty good results that you could view once your simulation is complete. If we look here, this is the surface pressure, and this is showing areas that have high pressure and areas that have low pressure. We have surface friction, and we can actually see how the flow is traveling over the body of the vehicle. Now, this would be really good if we start to look for areas where there might be separation or sort of laminar flow and start to do some on-car testing once this thing is completed to see whether these patterns are matching up in real life. We can show some streamlines of this and how the air is traveling. Well, this is an area where I'd really like to just be able to select something like the radiator area and just show the streamlines for that. Otherwise, with this resolution, it gives some idea of what's happening. You can see some areas of separation, but I didn't find this to be as useful as some of the other outputs. Now that can be done both vertically and horizontally. It does give you a good idea of where the air is traveling. Now of more interest is the 3D pressure clouds and the noise. So we see with the 3D pressure cloud, this is showing regions where there's a big transition to a low pressure region. And we see that the noise is actually doing a similar calculation of this. So this is a static simulation. So the noise here, this is an approximation of the noise, but it gives you an idea of where the noise is going to be. And unfortunately, one of the design goals was to try and avoid noise being at the driver's head. And if you look here, the driver's head is right in a big mess of noise. In fact, if we go back to the surface friction thing, we also see a fair bit of surface friction on the driver's head. So yeah, not a really fun experience for the driver in this car at the moment. So something to work on. The other thing that we see is some basic numbers, some basic forces. This gives out a frontal area, planform area. We also see a drag coefficient and a lift coefficient. And that lift is broken up further into the front lift coefficient and the rear lift coefficient. So we see where it's converged and the number of cells. So we see in this run, this was 11.5 million cells. Now, one thing that's really cool with this is we also have forces that are shown, and we can do this for individual elements. So for instance, I can grab the helmet of the driver and see what is the force that's being applied there. And we see overall a fairly low drag force, although it is noted that this is sitting in a really turbulent region. We also see that there's a bunch of things that we can download here. There's a PDF report that we can get all the simulation data and force data as well as the original model that was uploaded. And this is where I was once again impressed. See, in the past, a few friends and myself were running a company where we would do finite element analysis and other engineering design and so on for people, and we would produce engineering reports of the results. Now they go into a fair bit of detail, and they are designed, these reports were largely designed for engineering companies, but I know how much effort goes into creating a well-presented report that clearly summarizes results. And I was blown away by what I saw from AirShaper and the fact that this is a nice standard report. It gives all of the basic details of the simulation, so everything that was included in there, the type of solver, turbulence models, number of cells, and so on. And we see the basic views of the vehicle. So this is really just showing and running through how was the simulation set up. Then there's a performance analysis, and this is telling you what each of these things means, as well as giving the results. It gives some details of the simulation, so it is showing some of the convergence. Now, I would like to see some details of the mesh, but I fully appreciate that that's a very difficult thing to automate. Given the model, you might just want to zoom in on certain sections to show some of the mesh details that would be different from one model to the next. So it's not really something that could necessarily be put into an automated report like this. Now they do provide the opportunity to output data that you can then open in ParaView, and that's something we'll look at a later date. It also provides some comparison. So we can see that the drag coefficient actually says that Project 171 is closer to a bus than it is to a car in the way of drag, and gives an idea of the required power. So we see 8 kilowatts to overcome just the aerodynamic drag at this 100 k's an hour. And then there are some standard views of each of the graphs that are provided online. And this is very similar to how we would present results if we were doing an internal summary of aerodynamics for things like the Formula SAE car that the students would work on. It also gives you a little bit of an idea of how flow analysis is done, providing some pretty cool images to help with that, and then showing those streamline images. Now, for this project, those streamlines, it just didn't have the depth of information, but for some projects, it'd be really, really valuable, especially in a closed roof car. But in this, it's just a pretty dirty vehicle in terms of aerodynamically dirty, given that it is open top. And so there's a lot of things that are disturbing flow. So we're not seeing that those streamlines are getting reattached. But you can't doubt that these images look cool. We also see some section views, which are pretty handy. And I think these 2D velocity sections, this is giving that information that wasn't really there for this model on the streamlines. And you can clearly see some of this area of separation. Now, I was pretty impressed with the images that were chosen for the noise and how they were presented. And you can clearly see the problem that we've got with that noise and turbulence around the driver's head. So there's a lot we've got to do with that windscreen area. Now, to my mind, if all you got out of an analysis was this report, it would be well worth it. There is so much information here, so much to go by. The fact that you can go online and zoom around and look at all the little details, it's just so much information that you have access to when you're finished. And that's not even going into the fact that we can then open this up in ParaView and do whatever we want with the data. The data file for the full results is 1.6 gigabytes of data. So it's been a really easy setup, no problems at all in the calculation, and fantastic visualization of results at the end. Now, as soon as I reached this point, the first thing I wanted to do was go back in and to make some changes. You wouldn't believe how much self-control it took to actually sit down and try to make a video over this, rather than just get in and start playing around. But it is worth taking some time and saying, did we hit the goals that we're after? Well, I thought to start with, I might just use some other information that AirShaper had made available. So when going through to the simulations, not only do you have the simulations that you've run, they provide a whole heap of sample simulations and public simulations. There is so many results that you can have a look at. So what I thought I would do is I'd go through those sample simulations and have a bit of a look at them. So I went through all 160 of these and looked for the ones that were cars. And for every car that I found that was a unique one, I grabbed its details. So what was the coefficient of drag, what was the coefficient of lift, frontal area, and so on. And I could see, where does Project 171 sit in relation to all of these other vehicles? So plotted here, I have a series of points that are all of these vehicles. And this is showing their lift versus their drag. And you see that Project 171 is sitting right in the middle. Now this fella over the left, that is Superfast Matt's car. Very, very low drag. It's built for really high speed. This little fella down the bottom is a prototype sports car. So this looks pretty good. And the numbers suggest that. The drag coefficient was 0.44. The lift coefficient was 0.01. So this is really good news. I wasn't too worried about drag, but I did want the lift to be roughly neutral. The downside is there is a slight amount of lift, but this is pretty insignificant. What was a little bit more worrying is the front had downforce, but the rear had lift. Now the front has a downward sloping region, as well as a cooling opening that's picking up a fair bit of flow. Now, one good thing from this is it doesn't look like we're going to have an issue getting the front lift coefficient where we need it to be. It's already got more than we need in terms of downforce. We might add a little bit to clean things up and get the flow a bit more improved as it goes over to the back, especially the underside of the car. But otherwise, it looks like this is not going to be a front limited vehicle. However, the rear has lift. Now this is because we've got some fairly curved arches over the rear wheels, and these curved surfaces on the top are going to provide lift to the vehicle. Now I was trying to counteract that by putting in a bit of a diffuser, but really this diffuser's not working. And that's probably because we're getting a lot of leakage from the rear wheel well into this diffuser section, as well as not really having a lot of depth there anyway. So this is an area that I'm going to have to do some work on if we want to avoid something like a rear wing or a duck tail, if we're going to try and get that rear planted down at speed. So at this stage, looking pretty happy. But one thing to note is that for all of these cars, just about everything to the right of Project 171 is a racing vehicle. And if we remove all of the motorsport orientated vehicles, we end up with this. And here we see that Project 171 against all the other cars there, it's pretty horrible when it comes to drag coefficient. In fact, the only car that was worse was a tuk-tuk. Now, admittedly, all these other cars were closed vehicles, but it looks like Project 171 is horribly inefficient in drag. Except, that's not the whole story. You see, there's one thing that goes in Project 171's favor. Now, if we look at the equation for drag, the drag force is a half rho, so that's the density of air, coefficient of drag, times frontal area, times velocity squared. And this is where Project 171 does have a pretty good advantage. It is small. In fact, if we compare it to a scan that we took of me a while ago in a previous video, you get an idea for the scale of this vehicle. This is a small car. And if we show that the cars that are collected there and we show their frontal areas, Project 171 is smaller than all of them. So if we show the lift and drag forces at 100 kilometers an hour, we see that the car's actually pretty good. Not great, but pretty good. But there are plenty of areas where I think we can reduce drag, improve our lift and balance without really compromising the appearance of the car. So I'm pretty excited by all of this. I wasn't planning on doing this Aero work so soon, but I really appreciate that Visme at AirShaper reached out. This has been very interesting and has given a lot of development areas to work on. Now I do plan on doing future runs. Clearly, the noise around the driver's head is a big problem. And another thing that I need to have a look at is the yaw stability of this car at speed. That's something that I think I've experienced as being a problem in the Austin Healey. Another thing to do, and just with these results, is to have a look at a few more details of what we've got in ParaView. But I'm going to leave that for another time. Now, as some of you are aware, we do have a Patreon that is attached to this channel. Haven't really been posting a lot in there, trying to increase the frequency, but it is a place where, when we can, we'll put up some details, some content that you see in these videos. And from this analysis, I'm going to upload that report. I think it's well worth having a look through. So if you are interested in getting the report and some of the other files that we've been putting up there, feel free to go and join the Patreon. We will be showing more of this aerodynamic process on the videos, and we fully intend on keeping everything that we do on YouTube easily accessible to people. I also encourage you to go to AirShaper. They've got a lot of content there. You can check things out, see whether it's something that's going to be suitable for you and your projects. They have opportunities there to try it out, as well as a few samples for you to have a bit of a look at. But regardless of whether you want to pay for their services or not, it is well worth checking out all of their video content. They have got a huge amount of information about aerodynamics and in particular CFD. And I'm a big supporter of people that are sharing real engineering information with people online through YouTube. So I'm really keen to hear what you've got to say about this project and things that we could look at, whether it's comments about the model and the direction of the car, or aerodynamic things that really we should be looking at or thinking about. Really welcome the comments. They're always good to go through and always keen to respond to those. But I will say we're just at the beginning when it comes to aerodynamic content for this channel and for this vehicle. Thanks for your time.